Welcome to this lecture. In this lecture, I'm going to show how to derive the, the one-dimensional heat equation in differential form. Usually, any differential equation or any physical phenomena can be modeled in two ways or two forms. So one is a differential form, other one is an integral form. So differential form will follow Eulerian approach and integral form will follow Lagrangian approach. So in this lecture, I'll use the first approach, that is uh, Eulerian approach, to derive one-dimensional heat equation. So to derive this heat equation, let us consider a one-dimensional thin rod, so of length L. So it is placed along x-axis. So from starting from x is equal to 0 to x is equal to L. Let this material is made up of a homogeneous material. That means it is not made up of any composites. So it is made up of only single material, and hence all the physical properties of the materials like the specific heat, conductivity and density are constant at every point in x direction. And let us consider dx or delta x is this small slice of this material, where dx is this small slice. So so this is a one dimensional rod, so which is insulated laterally. That means outer surface of this rod is insulated, and so that there is no heat evaporation or heat loss in the y direction. That means heat only heat transfer takes place only in x direction. There is no heat transfer, vertical heat transfer. So to make sure that there is no vertical heat transfer, the lateral surface of this rod is insulated, but only the ends x is equal to 0 and x is equal to L are exposed for the temperature variation. That means heat may enter at x is equal to 0 and leave at x is equal to L. So further we assume that the temperature is non-uniform here. The temperature of this metal rod is non-uniform, and heat energy transfer, we know that heat energy will transfer from the higher temperature region to the lower temperature region. So therefore, so if we have x is equal to 0, the higher temperature, and x is equal to L, the lower temperature, then heat transfers takes place from x is equal to 0 to x is equal to L. Then how to represent this heat transfer or heat conduction or heat diffusion through this one dimensional solid? So we use the following three physical principles to derive this one dimensional heat equation. The first principle we use is heat energy or thermal energy of the body is uniform, is having a uniform properties. So heat energy is defined as the product of the temperature into specific heat into mass. So C into M into U. So where M is the body of the mass of the solid body, and U is the temperature on it, and C is the specific weight of that material. So units of C are L power 2, T power minus 2, U power minus 1. So where M, L, T and U are basic units of mass, length, time and temperature. C is the energy, specific heat required to rise unit mass of a substance for unit temperature. For unit temperature. So that is the first principle is used to derive this heat equation. And the second principle is Fourier law of heat transfer. So Fourier law of heat transfer states that rate of heat transfer is proportional to negative temperature gradient. That is, rate of heat transfer for area is minus k naught times dou u by dou x. Dou u by dou x is the temperature gradient, and minus k naught. So temperature always temperature transfer, heat transfer takes place from higher temperature to lower temperature. So because of that, the negative sign is taken given here. Here k naught is the thermal conductivity, so having the units, so M L T power minus 3 U power minus 1. So this represents that heat transfer takes place from higher temperature to lower temperature. And the third principle used here is the conservation of energy. That is, energy at any given slice is just depends on how much energy enters and how much energy goes out of that slice. That is the temperature, amount of temperature enters any part of this rod. He is always uh, must balance the amount of temperature going out. So because of this, let us to derive this, let us consider a thin slice of a rod of width delta x between x and x plus delta x. This slice is so thin that the temperature throughout this slice is u of x comma t. Temperature on this small slice is u of x comma t. Thus the heat energy of this segment is given by rho c a times delta x times u, so that u is function of x and t, so that we can write it as rho c a times delta x u of x comma t. So this is a product of specific heat density, the area element and delta x, the length of that the length of that slice times the temperature. And then by conservation of energy, we can write change of heat energy of this small segment for any small time delta t is equal to heat in from left boundary minus heat out from the right boundary. So then, following a Fourier law, so this the change of heat energy of a segment is given by rho ca times u of x comma t plus delta t delta into delta x minus rho ca times u of x comma t times delta x. So this is a varying with respect to time is equal to right hand side heat in from left boundary by Fourier law is a times delta t minus k naught dou u by dou x at x minus the heat out from the right boundary of this small slice is minus a times delta t times minus k naught into dou u by dou x at x plus delta x. So then, so we know that by our assumptions, density, specific heat, cross-sectional area, thermal conductivity, all are constants. This we can rearrange it as by cross multiplying delta t to left hand side, and this rho ca is common on left hand side to right hand side, and area capital A get cancels on both sides. We can write this as u of x comma t plus delta t, this term, minus u of x comma t, this term, divided by delta t is cross multiplied here, is equal to, so k naught, so k naught is common here, divided by rho c is cross multiplied from left hand side to right hand side, is equal to, this is dou u by dou x x plus delta x. So this becomes positive, minus here, dou u by dou x at x plus delta x comma t minus, this is negative, so dou u by dou x at x comma t divided by this delta x common here and cross multiplied to right hand side here, so divided by delta x. So we get this. So this is, you check, it is just a definition of derivative. So this is varying with respect to time. So t plus delta t minus this is u of x comma t divided by delta t. As delta t tends to delta t is very small or tends to 0, this left hand side is the derivative of u with respect to t. Since x is fixed, this becomes partial derivative of u with respect to t. And right hand side k naught by rho c is some constant, dou u by dou x, so x plus delta x comma t minus dou u by dou x x. So this is changing with respect to x and t is fixed, so dou u by dou x is a partial derivative and this is a dou u by dou x is partial derivative divided by delta x. So this is the uh, so difference between partial derivatives are two different points divided by delta x. As delta x tends to 0 or very small, this becomes dou by dou x of dou u by dou x, so that is nothing but dou square u by dou x square. So that is dou square u by dou x square is given here, and this k naught by rho c is called the some constant, material constant, represented as k, and it is called thermal diffusivity. So this equation dou u by dou t is k, copper times dou square u by dou x square is called one dimensional heat equation, which represents the heat conduction in one dimensional thin rod with the assumptions mentioned at the beginning. So this is called heat equation. Thank you.